Okay, guys, just to prepare, we'll be skipping some slides probably. This is comfortably fills an hour. You get 40 minutes, but we'll manage somehow. I won't introduce myself too much. My name is Stefan Siprell. You'll find the slides and everything later. I work at Codecentric, and if the doors are sealed, I'm a sales guy. But don't worry, this is going to be a pure technical talk, but this is what we do every day in our pre-sales. I've done this in various technical conferences, and I've never been thrown off stage, so please endure. Who's heard of SMAC? Okay, I'm surprised, as after all, this is the buzzwords. Do you know fast data as opposed to big data? Okay. Fast data, it's been coined by TypeSafe, the company, or not TypeSafe, Lightbend, and it's a stack consisting of 5 different technologies: Spark, Mesos, Akka, Cassandra, and Kafka. So it's basically kind of like LAMP. You had Linux, Apache, MySQL, PHP, or Python. This goes the same direction. There are 6 different tools. They're not too powerful alone, but you can do pretty cool stuff with them together. So let's look at the tools first. Who knows Spark? Okay, good. Actually, it's not a Swiss Army knife for data. Spark is a distributed computing platform, but the ecosystem of Spark is pretty rich, and most of the ecosystem resides in data. So if you're doing ETL jobs, extract, transform, load, you can do this very nicely in Spark with the batch topology. You have a Spark cluster, you can maintain it 24/7, you just deploy your jobs on it, and you have a real enterprise-level ETL suite. You want to do micro-batching on streams? No problem. I mean, we heard a lot about Flink the last couple days, about the big fight about latency and throughput. If throughput is your game, if you can wait seconds for results, Spark can make you happy. Running SQL and joins on non-relational database systems, no problem. So if you have a BI department who's used working SQL, if you're using something like Tableau or whatever, you can talk to Elasticsearch, Cassandra, whatever you want to, using the SQL dialect. Running graph operations on non-graph databases ain't a problem either. Last but not least, MapReduce and super fast, thank you. But I'll skip the Spark stuff as you're deeply involved with that. Mesos or Mesos. This is always Spark, everybody knows. Mesos is not as known. I think it's a pity because it's a really cool technology. If you look at the operating system, what the operating system really does, it manages resources. So you have 200, 300 processes running, and the processes are sharing the same CPU, the same memory, the same network card, the same mass data, and the operating system schedules it. It makes sure that each process thinks he's running alone on the system, and he gets the resources he needs. This is what one operating system, what kernel does. Mesos does this for a data center. So every resource you have, if it's hard disks, solid state disk, network cards, memory, CPUs, is managed by Mesos, and it makes sure that your processes running in the cluster in your data center gets the resources it needs. So the nice thing is, if you have a Mesos deployment, what you do, you install the Mesos slaves on all of your machines. It's one image you deploy on all of your machines. And during the workload, Mesos will decide how many instances of which process to run on which machines. So if you're thinking about big data, auto-scaling, resilience of failed nodes, Mesos is your friend. He can make sure that the right processes are going to be run. As opposed to VMware solutions or to Docker solutions, you're very open here. You can use whatever you want to. Hadoop, Kafka, Spark, and Akka, they run as native Java jobs on the host operating system. There's no virtualization, no isolation, no containerization. You're just starting up the jobs. So you have very efficient processing. And again, Kubernetes, I think they just released the newest version where they say you can have up to thousands of pods. You never had this limitation in Mesos. You could always run data centers. Akka. Okay, this is my weak spot. The beauty of Akka is you can create these highly performant reactive applications. So you just think of your application as just the big tree of actors working together in an asynchronous fashion. It's highly performant because any machine can take over any request. Concurrency is built in. You always work with messages in your mailboxes. It's elastic, no single point of failure, yada, yada, yada. Anybody looked at Lagom yet? The follow-up of Akka? Okay, nor have I. Then I have nobody to talk to later. And we're talking about big data, so let's talk about big performance. The beauty of it is you're working asynchronously. An actor is communicating to its other actor via asynchronous messages. If you do this in a typical JMS environment, you would limit the number of messages you're putting over the bus because the messages are very expensive because of transactional behavior, etc. You don't have to worry about this if you're working with Akka because you can actually send out 50 million requests per machine per second. So this whole delay, send a message, never hurts in the Akka environment. So we covered the S, the M, and the A. Let's go to Cassandra. Known? Okay. Cassandra is a performant and always up NoSQL database. It throws out a lot of garbage from the RDDS world. So it doesn't try to do transactions. It doesn't try to do foreign key constraints. It doesn't do a lot of kind of stuff you're used from databases. And therefore, what's left of Cassandra is super fast. So the rule of thumb is 10,000 requests per machine per second. This is insert or read operations, so don't really matter. There's no downtime because Cassandra doesn't have a single point of failure. It doesn't even have a single data center of failure. If you have multiple availability zones in your cluster, Cassandra can spread across these and survive a down of availability zone. It's a column index, so you have something like SQL, which smells like SQL, but you have the append-only performance. So any operations you're doing is actually just an append-only mechanism, so that's why Cassandra has such a nice sweet spot in mixing read and write load. Multiple data centers, we have that covered. And anybody who worked with Cassandra, it's really mind-boggling because the first couple of weeks you always want to normalize. You always want to do a join statement. You always want to say, but I already know the customer. I'll just join it from this table. It's wrong. What you want to do in Cassandra is you want to have denormalized modes. So every time you're thinking of a new query, you probably end up writing a new table in Cassandra. This is where the performance comes from because it's not doing any of this of this joining and resolution of normalizing. Okay. We'll have the last part covered in a second. Kafka. Can't do anything with Kafka nowadays. It's messaging for big data. I just mentioned this before. ActiveMQ, I worked with this a lot in the past, Apache ActiveMQ. The problem is it wants to have guarantees. It wants to guarantee the client, the consumer, your message is being processed exactly once. This is expensive because what ActiveMQ will do in a cluster mode, it's going to use the database for log handling. Okay, so every time you're pushing or reading something from the data from the queue, you're going to have hits on the database, and this just does not scale because you're trying to avoid relational databases and you're getting them back in here. So what Kafka does, Kafka can consume hundreds of megabytes per second and then push them to next clients, and it also breaks down the data to manageable volumes. Also, since you're in append-only mode, you can safely buffer terabytes of data without a performance hit consuming the data, because it's just pushed behind the old data. And obviously, it's distributed from the ground up. So now we just saw these loose technologies. Most of you heard of them, I think, except Mesosphere. So there's nothing new I can give you in the talk up to now. But the question is, what do we do with this? And in the beginning of big data, from my point of view, 6, 7, 8 years ago, everything was Hadoop. Okay? Hadoop was the first system which actually allowed to do big data. Big data means that the instructions go to the data and get processed locally as compared to the old database model where you had to load the data into memory first to process this. And you're breaking this paradigm. You're turning it up and around. And what you did in the beginning was always MapReduce. You were in a purely big batch mode. I think this is the first examples of MapReduce were the PageRank calculations of Google. This was the perfect example that you MapReduce, crunch your data at night. Business kind of learned, okay, well, it's kind of neat. I can classify my customers. I know that Stefan is probably a father because he's constantly buying Blu-ray videos of Snow White, but he's also a nerd because he's still buying his Magic the Gathering cards. So Amazon kind of learned new stuff about me. But the business always wants to find out this stuff faster. It wants to know, Stefan is still in the checkout queue. What can we show him? We just noticed in Stefan's bank account statement that he's moving money around. Maybe you want to interrupt it and see if you can take the money from him. And this is what we've seen so far as consultants, is that the latency between sensor reading and insight has to become faster and faster. Obviously, the Hadoop ecosystem reacted to it. MapReduce is not the only mechanism they have nowadays. Storm, Spark, a lot of these technologies also work on the HDFS, but we're looking at SMAC today. On the other hand, so we had the slow overnight batch runs with MapReduce. On the other end, we have this high frequency processing. So this is like high frequency trading in the stock market. You know, when you swap stocks 1,000 times a second. If you're monitoring a continental power grid, this is very demanding to find out exactly how much watt or ampere do I need in my system. Monitoring data centers. All of these are processes where you actually have guaranteed execution time of milliseconds. You have to promise your customer, you have to promise the client, you will execute in milliseconds. Obviously, this can only be achieved by being very sloppy and working on a very small context. If you have to respond in milli or microseconds, you can only use the L1 or L2 cache. So a very limited data set or very limited context you can work on. And it's sloppy. Before you lose the cadence, before you trip and fall, you're just going to ignore the request and take the next request. And this is something most of our customers are not willing to do. So the sweet spot for me, for SMAC, is everything in between. You want to react in seconds, yeah? But you want to react in seconds on a big context. You want to know, what did Stefan do in the past? What is Stefan doing right now? You want to have a big context, and you want to work in seconds. And this is, for me, the sweet spot where I would see SMAC. So examples would be updating news pages, classifying users. Is this a valuable user? Is this a fraud user? I've seen this a couple of times today, yesterday, real-time bidding for advertising, automotive in IoT, we're doing projects, or Industry 4.0. These are the typical use cases. The machine is behaving oddly. Is this having any effect of my output? These are second decisions. Does that make sense so far? If you don't say yes, I'll just repeat myself. Okay, so let's get to the juicy parts. What do we want? We want to have reliable ingestion. Reliable ingestion means that when your data producers keep producing data, and you have a little hiccup in your system because you cannot consume the data fast enough, because your system crashed, because the data scientist made a new algorithm which doesn't scale as well. All of this kind of can create trouble, okay? And then you want to be able to handle this trouble. We'll get to this in a second. You want to have flexible storage and query alternatives. The talk we just heard before, how you can build graphs on the fly. Some problems are really easy to solve if you consider the problem to be a graph. Some problems are really simple to solve if you see them as a number of tuples you can do MapReduce on. But you don't want to be limited by your database choice. You want to pick the database which is the right one for your job. And you want somewhat a management out of the box, okay? If you've ever set up Kafka, if you've ever set up a Spark cluster, these can be royal pains in the neck. And you don't want to do this all the time manually. You don't want to monitor this manually. You want to have some kind of management features. So, what is Mac? It's an architecture toolbox. We'll look at the architecture in a second. It's a best-of-breed platform. We've seen customers who don't use Spark, who use Flink. We've seen customers who use Droid or Elasticsearch of Cassandra. It's open. Do whatever feels best for you guys. It's just an example of how you can set up. Mesosphere introduced Infinity. This is a new tool from Mesosphere. That's the company backing Mesos. And they have all these tools already pre-integrated as a binary. So, who's done microbatching in his life? Okay, I already feel a little old school. Everybody's doing Flink, where you process each event individually. Microbatching is a little different. I think it was a good example. If you think of stream processing, you can have like a pipeline. If you think microbatching, you're thinking little buckets. So you fill your water in your bucket, and then you can process the bucket as a total bucket. So what you're doing is you're taking the stream and you're creating windows or static versions of this, and then once the bucket is full, you can see the bucket and you can process it. We typically use microbatching to establish a context. This means I want to find out what's happening in my environment. I don't want to react to the environment, I just want to know what's happening. How many, do I have any bots on the system trying to give me wrong recommendations? Do I have users who are trying to brute force login? Are there any specific categories or products which are selling really well on my website? This is something we just establish context, which is purely passive. So what Spark will do for you, it'll take events and it'll generate these RDDs out of it. RDDs is a concept known to everybody. Okay, I'll just do a quick version. The RDD is a resilient distributed data set, and it's a data container distributed across a cluster. And it's sharded across the cluster. And the RDDs, they have like relations to each other. You can say, this is my basic query. I do a filter operation, I get a new RDD. I do a map operation, I get a new RDD. I join it with other data, I get a new RDD. And so you have a whole cascade of RDDs belonging together. And this is the basic work unit in Spark. You can fill the RDDs whatever you want to. If you have Kafka, go ahead. If you have a database, you can pull it. The new versions of Cassandra, they're going to even support triggers, so you can actually have like a stored procedure running. You can have Akka or any other stream filling your data stream. These windows, they can be flushed to persistent storage. So what you can do is you can run your aggregations, you can do your classifications, and store the data with the high information load. You can extract that from the windows. You can also query them. You can query and modify them with SQL or in memory, for instance, or you can save the results again. So what I'm trying to say is, any kind of events, you just window it and you do your aggregations on it, and this is the context you can work with. If you know this user is looking at different products he looked at in the past, you can probably assume that something changed in his life. If you see that that a user is trying to hack the system because he's giving wrong IP addresses, you can react to this. Another nice thing is, we've seen this quite often, is in the project, it's not always clear when do I do a calculation. In the beginning, you want to do everything in memory. But then after a while, you realize you're building such large windows, you're having so much memory and data, that the application is getting sloggy. So the developers will always be shifting logic around between stream processing and batch processing. The nice thing is, if you're working with Spark, I assume this is the same with Flink nowadays, is if you're having an aggregation, and the aggregation runs on the fast lane or on the batch lane, doesn't really matter because it's the same API. So what we learned is that this flexibility between moving data from fast to slow lane or operations happens more often than you expect. Okay. Now we have a feeling that I know what's happening in the system. I know if I have any fraudulent users. I know if I have any bots. But it's not enough to know that something's happening. You have to act upon this. Okay? So when you found the bot, we want the bot to stop. When I've classified my user, I want to decide which ad do I want to show, which upsell offering do I want to show. And this is pretty much where we typically use Akka. So what we can do is that when we get the request, show me an ad or show me an upsell, we give Akka the request, let Akka handle it. Okay? And Akka has some pretty strong friends in the background. You can go to Spark, you can go to Cassandra, and ask him, give me a context. Okay? And Akka also has a nice way that since everything's asynchronously and passed down, you can actually deal with your own timeouts. You can tell Akka, okay, Akka, ask Spark what Stefan is looking at right now. Stefan, ask Cassandra what he did last year. And if I can't make up my mind, or if Cassandra is too slow, or whatever, I'm going to make a best effort estimate and just give him the product which we've shown the most time, or which we sold the most time. So with Akka, you can build these hierarchies of strategies and how to deal with a request, and also have them work in different service levels. Does that make sense? If you don't say yes, I'm going to repeat it. Okay, at least some nods. So, we mentioned the whole problem that we want to have a reliable ingestion. It's in the old school, when I did enterprise Java, it was typically you had a couple thousand requests per hour, and if the requests would collect over the while, it was okay. Okay, because if you're storing millions or thousands or billions of rows, it didn't really hurt you that much. The problem is nowadays there's so much load, so much data being passed around, you have to be a little more careful. Yeah, if Friday night a system crashes and it's filling your FTP server with 30 gigabytes an hour, you probably have to react over the weekend. Okay, because the boats are getting bigger. You're dealing with, and the bigger the boat, the better it is when it sinks. So, the core concept of this whole system are the reactive streams. Anybody heard of them before? Okay, it's going to be boring for you guys. I'm sorry. The basic idea is you have three different kinds of streams. There's a direct stream. I'm not going to dive into this between Kafka and Spark, but there's something like the raw streams. This is what we typical Java developers know. This is when I consume something from a TCP connection, or when I want to push something into a TCP connection. And the reactive streams, they behave like streams, but they have a much better backpressure support. Backpressure known to anybody? Okay, this is flow control. This is when you still had the old modems. You could adjust the flow control if you wanted to have software or hardware flow control. The flow control tells the system, stop talking to me. I have enough information right now. Okay, this just means that my buffer is full. It's saturated, and if you give me more information, I just won't listen to you anymore. So this is something which creates back pressure. If you're pushing data in too fast for the system to consume it. Basically, this is from physics, and the back pressure is if you take a straw and you blow through it, and the tighter the hole the straw is, the more back pressure you have. This is a back pressure in American, how's it called, wastewater system where the manhole cover's blown off. But we'll look at this in a second again. Just keep this in mind now. So, how does the data flow in and out of the system? Preferably over Kafka. Why? It's an append-only system. Again, this means that consumers may be offline for days. So if you write some kind of logic with machine learning which processes your data, you want to have the data coming in over Kafka. So in case your machine learning algorithm crashes or whatever, you still have the data and you can repeat the analysis. You want to have a broker. A broker reduces the number of point-to-point connections. Your Akka job doesn't have to know all the other Akka jobs. It just has to know its broker and what topics to use. You can use routing on streams. You can multiplex and demultiplex events. An example was from the talk before. Sometimes it makes sense to monitor trains individually, so each train gets its own topic. Sometimes it makes more sense to analyze all trains of a certain mark, of a certain manufacturer. Maybe you want to multiplex your events in a different kind of way. This is something which you can do quite elegantly in Kafka. We'll have a look at this in a second. You will have overloads, the different mechanisms you can react to this. You can either scale up on the hardware level, you can scale out on the hardware level, I'm sorry. You can also tell the client to communicate less, or you can just buffer it. And the buffer is the first line of defense. And the best part about Kafka is my point of view, the replay mechanism. You usually have a couple days worth of data in your Kafka system. This is especially nice because most big data environments I've seen so far, they have very little possibilities to do load tests in test environments, because you can't have a test environment which costs you millions of dollars a year. Most customers won't do this, so you usually do a lot of deployments directly into production, which is fine if you know what you're doing. If you deploy a broken algorithm which marks all of your customers as fraud customers, then you have a big boo-boo because they can't order there anymore. Fix your algorithm, replay the data from Kafka, and you can fix the data. Okay, I think this is the best part because I'm always relaxed doing a release in production when I know I can get out of it again. This is your ticket out. Okay, this is, I'm a German guy. We German engineers, sometimes it's really tough giving talks. And I had this one guy, and he talked to me for an hour after the talk saying Kafka was shit because it didn't support exactly once. Nothing works exactly once in distributed systems, so don't even think about doing it. Just write your systems idempotent so you can deal with double requests, okay? But this is probably for another audience. Okay. Cloud, bare metal. Who's running in the cloud? Public or your own? Okay. There are multiple reasons to do things different ways. Some customers, they have data privacy issues. Some customers are worried about their own IT department. But in the whole Smack stack, since you're running with Mesos, you can do both. Mesos does not require any virtualization, doesn't require infrastructure as a service. You can run Mesos directly on the bare metal if you want to. But if you have a cloud, you have redundancy and elasticity in it, go ahead and use it. I mentioned this before. You do not need any virtualization or containerization. So if you can, I would try to run tools like Kafka, tools like Spark. I'd like to run them natively on the host. Because there's no reason you want to separate there's no reason you need your own kernel. There's no reason you need to share your I/O ops with other processes. Just try to run it in bare metal if possible, but you don't have to. So, I think I'm doing way too fast. Let's see. Basically, you can do whatever you want to. There's no governing agency telling you how to use Mac. As I mentioned before, I try to use Kafka as much as possible. If you have systems which require a response in milliseconds because they're coming in over a WebSocket or they're coming over a REST service, you probably want to process directly in Akka and have Akka to do the service level agreements. But if this can be done later, always push it through Kafka. Your Akka can ask Spark. Your Spark can write and read from Cassandra to read and write from HDFS. So this is a lot of customers have different flows. Like one customer, they used IoT. They had a lot of data coming in. So we pushed them into Kafka. We would have a Spark job listening, which would create a repeat log in HDFS, so they could keep it over years. Could make sense, doesn't have to make sense. And as I said before, if you have a droid here, you can sit right here. If you have Elasticsearch running there or HBase, go ahead. Nobody's going to stop you. But it's important for me, at least. That's my 2 cents I learned from big data is the tools. They have very narrow sweet spots. They do very few things, but they do it very, very well. I grew up with Oracle and database in DB2 systems, and everybody told you use Oracle for any problem you had. But this is changing now, and this should reflect in your stacks. Does that make sense? Okay, look at the streams one more time. I think stream processing probably saw this slide in thousands of different variations the last 2 days. They're an unbound and continuous sequence of events. This means we do not know when that will end. We do not know how many events will be coming in, and all of this is open. And I think these shifts in load are very important as well, especially if you work in the IoT environment. You do not know when your sensors are going to fire. So, what do I do typically when I work with streams? I usually do not have this problem for long periods of time and threatening fluctuation in load. Usually when I deal with streams, I do custom buffer copying, I create buffered streams, whatever. This is what I usually did in the Java world, right? If I would use a buffer which is bound, I can survive more. Okay, when the client is pushing more data than I can process, I can always use the bound buffer. If it's RAM or if it's a hard disk or database, to say, okay, if it doesn't fit in my register anymore, I'm just going to push it off to another system. But these buffers can exhaust quite quickly. So the question is always, what do I do when the client is sending more than I can process? Do I drop the old data? Do I drop the new data? Or do I just reduce the sampling rate and ignore every 10th, every first, every second request? Now this is where reactive streams come in. They have a nice mechanism. In reactive streams, you have like a pearl necklace or a graph of consumers listening to previous consumers. Okay? So for instance, I know that Akka is working on the stream. It's doing some selects. Then it comes to me. I should write some aggregations to the database, and then I would pass the request on to the next system to do something with it. And usually, this works in the push mechanism. So the predecessor pushes events to me, and I just consume them. Now what happens is, when I'm too slow and I cannot process the data anymore, the predecessor is informed he's going to switch to a pull mechanism. So it's very human. So when I come home and my wife talks to me and I'm just overloaded, I tell her, I'll come to you and ask you in 10 minutes. Okay? And this is how the reactive streams work. And this And this mechanism, this failover, can go through the entire graph. So it can start in the very end, where somebody's not fast enough, and this failover of push to pull is going to go through the entire graph until the source. And the source has to decide what to do with this. Okay? If the source is some kind of Akka HTTP server, it has to know what to do. Do I stop listening to clients? Do I queue the results? But if your source is Kafka, everything's easy, because Kafka is capable of buffering these data for days and weeks. And as soon as your consumer picks up again because his congestion is removed, the whole failback is going to revert itself. It's going to fall back to a push mechanism. And these are the kind of nifty things which save your neck later in production. Okay, so it's not like you know the problems when you come to work and you see the logs are full of exceptions. You can see a lot of poisonous pills in your backlogs. What happened? You don't really know. The system here can help itself. Blah, 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 blah. Basically, the slide says that all of these components we talked so far use the same protocol of reactive streams. So you can, what comes out of Spark streaming, you can reuse again with reactive. Akka supports it, so you can, this whole flow topic is completely open. And as I mentioned before, Kafka is a perfect candidate for a bound buffer. Use it as much as possible. And Mesos can scale consumers on the fly during the fallback. So this is... 5 more? OK, I'm done in a second. What Mesos can do, it can scale up. So for instance, if you have a stream consumer which is trying to write to Cassandra, and Cassandra is getting too slow, Mesos can go ahead and do a scale up on your Cassandra installation. But this takes time. If you have a big Cassandra installation and you activate more nodes, it's going to rebalance the data, and it can take 30, 45 minutes. So in this time, where Mesos is scaling up, you can have Kafka covering your back. Then Mesos is going to be up, and then Kafka can switch over to a regular mode again, and you can work off the backload. Does that make sense? We've been a TypeSafe partner for quite some time, but we've never seen so much interest in Spark and Scala than since we've been working on Spark projects. And I don't think this is a coincidence. So streams love to be processed in parallel, okay? And streams love Scala. So every time you do something with Spark, you're in a Scala. I saw all the Flink examples were written in Scala because it has some features built in which are quite nice. You have this built-in preference for immutability. So when you work on streams, never manipulate the events. Create new events and push them down to another stream. This way, it's always reproducible what happened to the events. Scala has this notion of having a better support for functions. Functions meaning that you don't have any side effects of a function. If you look at a typical Java construction like a servlet, you can have instance variables bound to the servlet instance, meaning that a servlet is going to respond in different ways depending on when you ask the servlet. But you don't want this in functions. Functions should be neutral to any side effects. And another nice thing, this is when I started to love JavaScript, when you can use functions as first-class citizens and pass them around. I'll skip the inverted index example, but I'd like to show my kitten slide. Any questions? Any feedback, including, oh my God, this was boring, or...
One moment.
Thanks for the talk. Is there any real use case?
Excuse me?
A real use case you've applied?
A real use case for this Mac stack?
Yes.
What do you mean with real use case? Are you talking about projects we're doing? Are you talking? Yes, there are projects for this. It's.
Sorry, thanks.
I emphasize this really strongly about context detection and context reaction. And as soon as you have a problem where the context does not fit into a heap stack of the browser anymore, then you have a use case. So if you have a website and you're dealing with 1 million customers and you want to classify the customers, everything, you're probably better writing everything in regular Java util classes. But as soon as your context gets too big to decide on this on the fly or decide on this on one machine, you're moving towards this max stack then. That's my feeling. Please discuss. So our examples was we have 2 customers from the automotive industry where we're doing these evaluation of all the sensors the cars are delivering. We have 1 customer doing real-time advertising, and those are the most interesting ones at the moment.
Any more thoughts? Any more questions to add? Thank you so much for your
Thank
session.
you.